Hi everyone, and thanks for checking out this selkie project video. My name is Paul Bonner. I'm a senior engineer at Gavin and Doherty Geosolutions, and together with our selkie partners, we're developing open source tools to help with the design of foundations, anchors, and moorings for marine energy projects. Today I'm going to talk you through one of the tools we're developing, which will help with the design of gravity-based foundations and anchors. I'll start with a quick introduction to gravity-based systems, run through the design procedure we've proposed, and then show you the first version of the new selkie tool that we've coded up in Python. So as we know, gravity-based foundations use their self-weight as well as seabed friction to resist the loads and moments applied to the marine energy device. These systems are used in a range of offshore sectors, most often in shallow water, and are best suited to medium or hard seabeds. There are some more advanced models, so as you can see in these photos, there are steel frames or reinforced concrete shells which can be transported to site and then loaded up with ballast, but in their simplest form we can think of these just as heavy concrete slabs. The advantages of a gravity-based foundation is that it's simple and that with the right equipment it can be repositioned and reused with ease. The disadvantages are that some designs can use a lot of material and provide only limited resistance to horizontal loading. So what we're proposing for selkie is a simple decision support tool aimed at an early stage of development. And at this stage, I should credit my colleague Majid Hussain, our partner at UCC, who established this framework. So like the tools produced by the earlier DT Ocean and DT Ocean Plus projects, the selkie tool is going to use standard quasi-static methods and try to identify the smallest and hence least expensive foundation which passes the different design checks. The key differences will be the form of the selkie tool, so it's going to be a standalone Python code, and the fact that it has design checks for drained and undrained soil conditions to try and capture both short-term and long-term behavior, as well as options to embed the foundation or use a perimeter skirt to provide greater lateral resistance. So this is the basic flowchart. We start with our inputs, which we can get from the selkie GIS techno-economics tool or some other source, and then the tool goes through a pre-design stage before running through design checks for bearing capacity, sliding, and overturning. If the foundation fails any of these checks, we increase the size until we have a system that passes all of them. So this can be done through iteration to try and output the minimum size, but the user can also specify a range of sizes, and the tool will output all the results in a table for ease of comparison. So we'll go through the inputs now. I've grouped these into device data, location data, and then options. So under device data, we've got a characteristic size, which we can use to set the initial size of the foundation or anchor. And we've got our ultimate limit state forces and moments, which we can get from the selkie mooring tool or some other source. Under location data, we've got a list of seabed parameters. We're planning to get these from the selkie GIS techno-economics tool or a standard lookup table to try and make this as easy as we can for the user, and they're going to be able to adjust these default values as well. And then finally, under options, we've got the size range for our foundation, we've got the density and unit cost of our foundation material, and our safety factors, as well as our embedment and perimeter skirt options. So the next step is pre-design, which uses standard methods and assumptions from the sources on the right to do a few different things. First, the tool does a basic force resolution to calculate new horizontal and vertical loads, accounting for the slope of the seabed. It then checks for eccentric loading, which would reduce the contact area between the seabed and the foundation. And then finally, it establishes the dimensions ahead of the design checks. So in this case, we're assuming just a simple rectangular concrete slab. So these are going to be the length and width and thickness, but we'll also account for the depth of the embedment and the perimeter skirt as well. So with the loads and dimensions established, we're into our first design check, which is for bearing capacity. So this is just to make sure that our foundation isn't going to sink into the seabed that we place it on. So we've got two bearing capacity equations for drained and undrained soil conditions, and these are functions of a few different terms, as you can see, related to cohesion and overburden and friction, as well as a side traction term, which accounts for the embedment and perimeter skirt. Our applied loads then are the sum of our vertical forces, and we use our user-defined safety factor to make sure that the effective capacity is greater than these applied loads. If it is, we can proceed to the next design check, but if not, we can go back, adjust our foundation spec, and try again. So next up is the sliding check, which we use to make sure that our foundation won't just move along the seabed along with our device. So again, considering both drained and undrained soil conditions, we've got two equations for sliding resistance, and these are functions of the applied vertical load, the weight of the foundation, and a couple of different soil parameters. As before, if the effective capacities are greater than the applied loads, we can move on. If not, we adjust our foundation spec and start over. And the final check then is for overturning. So again, standard equations, but this time to make sure that our device and foundation won't just flip over onto the seabed. Our overturning resistance is a function of our applied vertical load, the foundation weight, and the seabed slope. And this is the final check, so if our foundation passes this one as well, we've got a design that meets all the basic requirements. And then once all three checks are passed, the tool will output the final dimensions, which can be used to inform feasibility or option studies. You can compare this foundation, for instance, with the equivalent suction caisson foundation that you can get from another selkie tool that's in development, or it can be used in a simple numerical model as the first step towards a more sophisticated design. We'd also like the tool to produce a capital cost estimate, but we're still trying to think of the best way to do this. In the demo version, the user can estimate the capital costs based on the volume of material and the unit cost, but we might also want to include other costs like seabed preparation for the sake of comparison. So these cost estimates will be useful in feasibility or option studies, and they can be fed into the selkie GIS techno-economics tool as well. Okay, so now that I've explained how the tool works, I can show you the first version that we've coded up in Python and run through an example. So here we're going to be sizing gravity anchors to go with a catenary mooring system for a wave device placed off the Welsh coast. And you can see here at the top of the code, we start with our inputs. So in this example, we've got a range of anchor sizes with lengths varying from 3 to 9 meters in steps of 0.25 meters. We've then got some soil parameters, which are broadly representative of a clay or a mud seabed. This is what's specified by the selkie GIS techno-economics tool in this case. And then we've got our safety factors for soil 1.3 and for our bearing capacity and our other design checks 1.5. We've then got our unit weight of concrete and our material cost. So this is in kilonewtons and euros per cubic meter. And then we've got our perimeter skirt and embedment options. So these are kind of hard coded for now, further down in the code as I'll show, but they can be easily changed. And then lastly, we've got our ultimate limit state loads and moments, which in this case we've got from the selkie mooring tool. So we've got a catenary mooring, and this means we are only transferring horizontal load to the anchors. In this case, that works out to be 230 kilonewtons, and we've applied a safety factor of 1.8 to account for the fact that this was developed using simple quasi-static methods. After this, we've got a couple of different blocks of code. I'm not going to spend too much time on these because I've gone through them on the slides. I thought it was easier to have a look at the equations there. But you can see that what we've got is a for loop, which will run through all the specified anchor sizes. And inside these loop, we've got different blocks to calculate the loads, test for eccentricity, and calculate the dimensions, and then to go through the different design checks for bearing, second bearing, sliding, and overturning. And then lastly, we've got two lines which are just used to present our results in a handy table. So if I've done everything right, this should run in just a second. Thankfully it has done. And then we can look at our results table, which we've got here. So if I try and make this a little bit bigger, make it easier to see, you can see that what we've got are our range of foundation, or in this case our anchor types. We've got length, width, thickness, we've got weight, and then we've got cost, and then we've got the results of our design checks as well. So you can see a couple of different things here. First of all, the smallest foundation or anchor which passes all the design checks is 7.75 by 7.75 meters. So that's obviously very large, but in this example we've also got a very large device and we've got some large safety factors as well. We can also see that sliding is the key design check, which is what you'd expect from a catenary mooring. We've had to increase the anchor size quite a lot to be able to pass this test. We can then go back to the code and adjust various parameters to see how these affect the design. So it's all here and it'll be well documented. You can change whatever you'd like, pretty much. So I'm not going to play around with this too much on the demo, but what I will do is I'll show you what happens if I turn on the both the embedment and the perimeter skirt options. If I run this again, it should run in just a second. And in this case, you can see how it's affected our results. So in this case, now we've got a minimum anchor size which is a bit smaller, so 7 by 7, and you can see here that this is how the tool can be used to compare different options. So by including both an embedment and a perimeter skirt, we can reduce the material requirement and hence the cost by about a quarter in this example, which is really useful to know. Okay, So that's a very quick run through what we're thinking for the selkie gravity-based tool. As you can see, we've got it reasonably well outlined, but we haven't finalized it yet. So we're still open to suggestions on how to make this better and more useful to the industry. If you've got any questions or suggestions, feel free to drop me an email. My address is there on the screen. Otherwise, you can keep an eye out for our next report, which is going to describe this tool in greater detail. Thanks for watching.